Sounds good. Right. Hi, everyone. As Ian mentioned, my name is Adrian Roman, and today I'm going to talk about how we estimate direction of arrival using a graph signal processing model for acoustic imaging. But before getting started, I would like to briefly talk about me. I am from Uriangato, Guanajuato, Mexico. I graduated from UC Davis doing my undergrad in applied mathematics and computer science. And I have industry research experience working as an audio software engineer. I write software, firmware, UI, and AI models applied in audio software. So the agenda for today, I'm going to talk about the graph signal processing model we use in this project. It is called DeepWave. I will also share how we leverage this model to estimate direction of arrival. And I will present a quantitative analysis and benchmarking we did of this model against other state-of-the-art deep learning models for sound event localization. And finally, I will leave probably like a couple of minutes for a Q&A, and maybe we can also discuss my ongoing research with this project. So DeepWave, as I mentioned, DeepWave is the graph signal processing model we use in this project. It is a recurrent neural network for real-time acoustic imaging. And something that makes interesting DeepWave is that it is a model capable of rendering high-resolution spherical maps in matter of milliseconds. So it's a very fast model. And DeepWave's architecture is also fairly simple. It's made out of these building blocks that you see here, the squares and circles. And DeepWave takes as input the raw audio signal from a microphone array. It can be an array of however many microphones. And it works over 100 milliseconds frames of audio. So for these 100 milliseconds frames of audio, it will take them and then it will compute a correlation matrix across the n different microphones in the array. Then it will go through a back projection module where it essentially takes this matrix and projects it into an image form. And this image form is essentially what we will slowly optimize with the different building blocks of the network. So we will start with an initial guess. This initial guess is the spherical map, but just random noise. And then slowly, via stochastic gradient descent, we will have a deblurring operator and a sparsifier. That this actually reminds me a lot of the modern diffusion models that slowly start getting rid of noise, audio artifacts, until we get to a nice spherical map. And the spherical map that it outputs, it looks like this, like the image you see below. And we have an elevation, we have an azimuth. This is a sphere. It's just the projection. This is a Robinson projection. And here we have that in this plot, you see two sources of sound, the white dots. And we see how DeepWave has two intensities. This bigger, maybe this sound is louder than this other one. And also we see two colors because DeepWave, the intensity map it outputs, it is divided by frequency bands. So we have a total of 10 frequency bands as the representation for our intensity field. And this is how DeepWave looks in action. We have two moving sources. This is people speaking. And as they speak, you can see how DeepWave highlights in this spherical map the points where it detects where the people are speaking. And this is actually the main reason why DeepWave is often called an acoustic camera, because you can visualize sound, which is pretty cool. So the problem statement is the following. Using DeepWave as an acoustic camera, how can we quantify its direction of arrival accuracy? And where does DeepWave stand compared to novel deep learning models for sound event localization and detection? Well, determining the direction of arrival, what we use is unsupervised learning. As I mentioned, DeepWave on the left, you can see all it gives you is just an intensity in the spherical map. And we know a ground truth. This comes from our data set. So what we do is, well, we know that there is an intensity. So what we do is we use k-means clusterings to localize relevant intensities. And here we are using 12 points. And for those 12 points, we apply k-mean clusterings with k equals 3. So it will generate 3 clusters, the orange circles that you can see. And through a heuristic that is called unify, we're able to further unify these 3 clusters. So we will end up with only one cluster. And given that we have a cluster, then we can find a centroid. And the centroid is the exact coordinate point in space that we want to predict. And it's like the purple point that you see here. So now that we have an exact coordinate point in space, we can actually apply localization metrics to see how good our model is doing. And for this project, we use the metrics proposed by the DCASE challenge, task 3. For those that are not super familiar, DCASE is a challenge where a lot of people in audio submit their models. The task 3 of the model of the project is for localization tasks. And these metrics are openly available on GitHub. They are also very well documented. And the 2 main metrics we use in this project are localization error, which tells you the angular distance between the predictions and the ground truths. You can think that the closer this value is to 0, the better. And localization recall, which tells you the true positive rate across all audio frames for our predictions. And again, you can think that the closer this value is to 1, the better. So now for the quantitative analysis, what we did was to compare our localization estimations of deep wave with the baseline model from the DCASE challenge. So the DCASE challenge has this baseline model called the SelfNet. And what we tried was to put the comparison as fair as possible. We know that the SelfNet can localize up to 3 simultaneous sound events. So what we did with deep wave was something very similar, using k-means equals 3 to localize up to 3 sound events. We also use the Locata dataset for training and testing. The Locata dataset is a speech dataset where people speak hardware sentences. And for deep wave, we use 32 raw audio channels from an eigenmic. And for the SelfNet model, we use the first order ambisonic format of the eigenmic. Now, something to keep in mind about these models, one is that, yeah, of course, the SelfNet is a very big model compared to deep wave. We have 500,000 plus parameters in SelfNet compared to 60,000 in deep wave. So moving on to the comparison, the first stage of comparison we did was just using the raw data as it is, training and testing. We didn't touch anything at all on deep wave. And what we saw is that in this first round of comparison, we see that SelfNet had a lot better localization error compared to deep wave. However, this made us think what can be happening, and we started thinking, well, one of the things that, of course, we know is that there's a lot more parameters in the SelfNet. Another aspect is that we haven't touched anything regarding the intensity field that deep wave is capable of inferring and outputting. And another aspect is that we are not considering at this point the voice activity of participants. So for the moments where there's silence, we are just using labels that say that there's an event, but in fact, there's no event happening. So moving on to how we improve deep wave. Well, we thought that the intensity field of deep wave has 10 different frequency bands. So what we thought is, well, what if we maybe add the frequency bands like these ones, or what if we square them or multiply them with each other to potentially highlight relevant sound events and get rid of some noises in the spectrum. And this actually got us to improve. Squaring the layers and adding them brought down the error to 35. And also we noticed that near the edges of the intensity field that you saw at the beginning, there's noise often. So what we used was adding a 2-key window to add some smoothing near those edges or poles. And this actually brought the localization error down to 29. Furthermore, something that we also analyzed was we pay attention to what was happening with the tracks, and we noticed that not all the time there's an active speaker. There's a lot of moments of silence. So we started thinking, what if we add the voice activity detector to our ground truth data? For those that are not super familiar, a voice activity detector tells you where there's an active voice versus where there's not an active voice, either silence or something else going on. And you can see it here with the orange line. So in fact, adding a voice activity detector as part of our ground truth labels was like the last step to make things as fair as possible. And with this, we were actually able to see a fair comparison. And we do notice that DeepWave performs in a very similar way as the baseline model from the DK's challenge. And actually, the localization recall seems to be a lot better in DeepWave. So in conclusion, we can say that DeepWave can be applied to perform direction of arrival estimations by using k-means clustering to localize relevant sound events in space. For up to 3 active sources, the localization capabilities from DeepWave are close and even equivalent to the ones we see in the baseline model from the DK's challenge. And another aspect is that DeepWave is a very promising model for doing many more applications, even in the real world. One is because it is very time efficient. In the paper, the authors mentioned that it's just as fast as a simple delay and sound beamformer. And another aspect is that it is very robust to drastic changes in sound events, such as moving sources or silence. And yeah, this is pretty much the end of my presentation. I'm open to hear any questions. Thank you for listening.
Thank you very much. So there's questions in the chat and I'm just gonna go through them, all right? The first one is, Magda is asking, does the training include the k-means post-processing?
Maybe I can explain a bit where my question was. Like, by the way, very, very nice presentation, very clear and very nice work. I was just trying to understand how you trained that model, given that the model is predicting this these intensity maps, let's say.
Yeah, yeah.
But the labels of locata, if I understand correctly, are points in space, right? Exactly. So I'm just trying to understand how is the model trained in that way. If it's like,
yeah, good point. So k-means in terms of training, it's not involved. K-means is just the method we use to extract the localization that the model is able to learn. Now, for actual training, DeepWave uses another model that is like the guide. It's called APGD. It stands for accelerated stochastic gradient descent. And yeah, this other model gives you the sound intensities, and from those, DeepWave trains as having that as the ground truth. Does that make sense?
Okay, so not directly the annotations, but it's like another model that's inferring the positions and giving that to DeepWave to guess to learn those mappings.
Mm-hmm.
So yeah, I'm just wondering, maybe, I don't know if as a follow-up of this, maybe that's a point to investigate, because you are using to evaluate.
DeepWave is so powerful that there's so many things I want to do. That's why I mentioned there's a lot of ongoing work. But yeah, I'm open also to any ideas. Like, this is pretty cool.
Yeah, that sounds something that I will be curious about, kind of like seeing how much that how much that is introducing error in like the labels that you're giving to DeepWave to learn. And maybe if you just introduce like a very like a small k-means or something that directly uses the the annotations from the data set, you might have a boost or not. I'm just curious.
Yep, makes sense.
Very nice. Thank you.
Yeah, so
Thank you.
we have another question from Eduardo Alves da Silva. Do you want to say your question, Eduardo, or should I read it?
Okay, I guess I can say it. Can everyone hear me?
Yes,
Okay. So yeah, first of all, thank you, Adrian, for such amazing presentation. I was just wondering if, like, since CellDNet, if I'm not mistaken, it also it has some recurrent neural networks at the end, which apply temporal context. And I didn't, maybe I missed something. Do you also use temporal context information to perform the tracking?
That's a really good question. We don't have temporal context right now in DeepWave.
Okay.
However, that's one of the features that I want to add in the network. I'm writing right now DeepWave in PyTorch. And the reason is to add a lot more features that I see the model is lacking. One is the temporal context. So essentially the model right now, all it does, it takes the 100 milliseconds frames of audio. And then for the next batch, it doesn't know what happened before. So what I want to do is to give that as the initial conditions, because I don't know if you remember, I mentioned it starts with an initial guess.
Initial guess,
So this initial guess will be the last step from the previous 100 milliseconds.
Yeah, it makes sense. It makes sense.
And I'm pretty sure this will also make the model even more robust to changes in moving sources, silence, and so on.
Yeah, absolutely. Yes.
Really good point.
Yeah. Do I have time for another question, maybe?
Go ahead. Go ahead.
Well, I mean, you kind of answered what I was also going to ask, because CellDNet also, it uses bidirectional recurrent neural networks. So it's not able to perform real-time tracking, right? But now with what you just said, you kind of solved it for me. Your model is able to perform real-time tracking. So yeah. Okay, yeah,
Yes.
it makes more applicable, right? Because most applications you're not going to be able to take the whole temporal context. You have to use just the previous, So yeah, once again, thank you.
They even have some demos on YouTube. I have some references and also useful resources. Yeah, I'll share it with you. They are kind of like cool just to browse around, but yeah, definitely.
Oh yeah, I would love that. Thank you.
No problem.
All right, and that is all the time we have for this talk. Thank you very much.